The objective of the session today is to do an exercise on electric submersible pump. And the exercise is assuming that the reservoir production strategy has been defined by by the reservoir engineering group, and our task is to verify with a pump that has been suggested by the vendor if we are going to be able to deliver those rates, if the pump will be able to deliver those rates. In our previous session, we have seen um, that the ESP essentially we have some pressure, some energy available from the reservoir, but we need a higher energy to flow against the rest of the system. So that's what we are essentially are going to do here. We have a pump model, we have certain characteristics, we have a motor, we have a performance map, and then we want to verify that that particular machine, that particular equipment is able to deliver the combination of Q and delta P that 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 I calculate. So the case study we're going to use it's and that's a paper by Baker Hughes and Equinor, Statoil at that time, and ESPs are not very common in offshore fields in Norway, but they are common some other places. In here, in this case, in Brazil. And this is the case study is a Peregrino. It's called the Peregrino field in offshore Brazil. Here you see the location and on the map, and Rio de Janeiro. It's I don't see it here, but it's close by Rio de Janeiro. Not well, not that close, but it's at least relatively close. And that's the layout of the field. The field has two jackets, two steel jackets, and then the wells are dry wells, platform wells, that they are drilled from the same location. You see here the drilling tower on both, and then they deviate and they reach different targets in the reservoir. So one of the characteristics of this field, it has a very large aquifer, and it has aggressive water injection to keep the pressure, to keep to maintain the pressure, and also the oil is very viscous. So I think it's 100 centipoise in reservoir conditions. So to be able to lift, to be able to produce economic rates from these formations, from this reservoir, then you need to have the ESP to provide energy to the fluid to bridge the difference, the pressure drop, the frictional pressure drop between in the tubing. And here you have an FPSO, which is for storage, but also you have the main separation of, I believe the main separation of water and gas is happening here, and then they return the water. The water is not dumped, disposed on the ocean, but essentially is injected back into the reservoir. So we're going to take data from this paper, and here you see the predicted or the planned production profile, and they have different type of producers. You see, it's not you cannot see very well here, but it's liquid rates versus time, and you have the green is oil plateau and then decline. Water, you have here water breakthrough starts to increase. Initially no water, and then the water reaches the well, and then it starts to increase. Then you have some other producers, low, medium flow rate, and low flow rate. I don't remember exactly which one I have picked, but I picked one of these. And then we have the characteristics of the pump, and here we have the flow map of the pump, and these are different models. Um, these are different models, but maybe this is better. What we have been discussing so far is that you have an operational area, and that's for a viscosity of water, 1 centipoise, and we're going to have to convert this map to the 100 centipoise viscosity. But essentially you have different models indicated with different colors, and you have the limits defined by the maximum frequency, minimum frequency, maximum rate, minimum rate due to upthrust, downthrust, reduced efficiency. Okay, and you see how, what is the area, operational area of all of these pumps. Just pay attention here that it says 1 STG, is one stage. So the pump is made by different stages. So you can take just one for one stage, and you simply multiply that by how many stages you have, and that will give you the performance of the pump. You have some effect that is called pancake effect, that it means that you lose some energy when you exit a stage and you go to the next stage. So that's not exactly linear. It's not simply a multiplication of all the performance of all stages, but you have some deterioration factor there. But we're not going to, in our model, we are going to assume each one of the stages are compiled, uh, are equal, and they contribute the same. Okay, more models. Uh, they have different pumps. And the last thing I want to show, that's the cable, power cable. You see here the down thrust, up thrust, the best efficiency point that I explained during our last lecture. In this case, the best efficiency line, the line of best efficiency points is not in the center, but is slightly moved to the right. And there was one more thing I wanted to show you here, was the completion diagram. So that's the more professional diagram that what I painted before. But essentially, you have the packer, you have the downhole valve, you have the capillary tube for the downhole safety valve, and then you have the power cable all the way to the pump. And here you have the packer that I told you, so you cannot produce any gas from the annulus. So all the gas has to go through the ESP. That's why it's important to keep the pressure above the bubble point pressure. And in this case, the ESP is located because the wells are deviated. They are drilled from the same location and then they deviate. So it's located in a deviated section. And ideally, you want to put the pump as close as possible to the formation, because then it has maximum effect. It closest to the source, then it can reach the difference of what I have downstream. But because the well is deviated, there might be some limitations how close I can be to the formation. If I start to be on too horizontal, if I have to become, if the pump is installed too deviated, then you start to have wear in the bearings, and then it will have a decreased life. Hmm? Okay, so let's see what we have on our Excel sheet, on our exercise. So we have here, that's the main window that we're going to work with. We have one well we're going to analyze, the initial reservoir pressure, the productivity index, that's for total liquid flow. That's the height, that's the difference in height from the formation to the suction, from the PWF to P suction, 380 meters. And the diameter of that is flowing casing, so it's 0.24 meters. And then you have the flow from the discharge to the pump to wellhead, 1960 meters, and then you have the tubing diameter. Number of stages I have are 78. The properties, oil and water, 1000 kilogram per cubic meter, 897. You have the viscosity of water 1 centipoise, oil 100 centipoise. And we are not going to talk about emulsion. We are going to do our calculations without emulsion. But remember that when you have flow of oil and water, you might, if you start from pure oil and you start increasing the amount of water in the stream, you see that the pressure drop increases, reaches a peak usually, and then it starts to go down, and it will reach the viscosity of the water at the mixture will reach a viscosity of the water at 100%, close to 100% water. So that's emulsion behavior, but we are not going to include it here. Then you have the roughness and the bubble point pressure 30 bar. That's what I have to be above that pressure to in the suction of the pump to avoid having gas liberation and, and bad operation of the pump. So before we go to each year, so you see here at the end we have the production data taken from that paper. What the only thing that paper doesn't give is the pressure with time, reservoir pressure with time. So here I have assumed a linear trend, okay, but most likely will be fairly, it will have a slight decline. And here is how the profile looks like, and I think this is for the medium producer. If we go back to the paper, okay, that's a medium flow rate producer. I think that's what it corresponds to. So a similar trend. You have oil, liquid, that's the liquid, but you have the oil. Essentially, initially you have a peak, it starts to decline, and then you have water breakthrough, and the water starts to increase. For our analysis, we are going to simply take some points in this region during the initial region. We are not going to look into when we have water production. But it is left as an exercise. If you want to verify the pump for other times, then you can simply come here and then pick some for the other water cuts. If you see, the Q liquid is increasing, which causes the pump to use more power, but the viscosity, when you're producing too much water, the viscosity will be close to the water. So there is like a balancing effect. If you have a high rate, but you have low viscosity, you're using some amount of power. But if you maybe have a lower rate, but then you have a high viscosity, then you use some other amount of power. So they compensate each other because high viscosity, you need more power, but also high rate, you need more power. But if it is left as an exercise, if you want to verify other points, here I have picked a few points. You have reservoir pressure, water cut 0, and then you have this. So here the density, what we and let's see what else we have on the Excel sheet before we go to. So we have let's go to the plot first. So here you have the performance curves of the pump. That's pump head. I told you that we work with head because it's with density, the performance map will change. But if I divide the delta P by density, then all of them should fall on the same plot. So that's the delta P divided by density. You have the curves at different frequencies. You see from 30, 40, 50, and 60. And then I cannot reach all the curve, but due to upthrust, downthrust, and efficiency, I have a minimum line, a maximum line, rate line, a minimum rate line, and the best efficiency line. So I want to be always close to this line because that's what gives me the best efficiency point. Remember that these rates is not in standard conditions, but is at the inlet of the pump. So if always oil has some compressibility, either because it has gas dissolved, so you have to be sure to use the rates at the inlet of the pump. In our exercise, we are going to assume that the volume factor is simply going to be 1. That is, the fluid is incompressible, which I think the GOR in this field is relatively low. Yeah, so how the curves were found by, you see here the points extracted from the paper, and then you fit it to a polynomial. In this case, the best fit was for an order 4. And then you have the efficiency. You see the head goes down with rate. You all the time want if you want to produce a higher rate, you will be able to increase the pressure, a smaller increase in pressure. But then you have the efficiency, in which you have a peak inefficiency, and then you have a sharp drop to the left and a drop to the right and a drop to the left. And this efficiency has been also reproduced with a fourth order polynomial. So those are the coefficients. If you see back to ESP performance of water, these are these coefficients that are shown at the top. A, 4, 3, 2, and 1 for the head and for the efficiency. And these curves are made for a given sorry, here these curves are made for a given frequency, reference frequency, which in this case is 60 Hertz. I told you how you change. You use similarity law to change from one frequency to another. You scale the head with frequency squared, and you scale the rate with simply this frequency. And then we have another interesting, so here you have for water, which we are not saying that the viscosity is 1, but then we know that we have a viscosity of 100 centipoise. So that is specified here in this sheet, and the data is in this sheet here. So we see that for water, that will be the performance, but when we have 100 centipoise crude, that is the performance. So it is affected very much, it declines very much, and that's due to the effect of the additional frictional losses that you have in the pump. And the minimum and maximum and minimum line are also affected, slightly affected. So you see that the area essentially is shifted down. It's just like scaled down from this initial square to this initial region, to this region. And the data is here, how the correction is made. We're not going to go into that, but there are many different methods that are used to correct. The best is simply to test the pump with the real fluid. But you have some correction methods available in software that they are supposed to do a fairly accurate work at predicting the new pump performance. So that's what we are using here in this example. We are correcting this with the guidelines and the procedure given by the Hydraulic Institute for correction of viscous flow of pumps. So see how it changed. So if I now change, for example, to 50, here I change the viscosity, and it should become closer to 1 centipoise. I think this procedure has a limit for how high the viscosity can be. It is valid only within a range. So what we are going to make is we have, that will be the applicable map for the pump, this map. So we want to make sure that our operational points are going to fall inside this map. And if not, we have to make corrections. Either we have to change the model of the pump, go back to the manufacturer, to the vendor, and tell them to give me a different model, or you have to reduce reservoir rates. You have to change the reservoir target rates. And it can be either because I'm outside on the high side, I want to produce a higher rate with higher delta P than what I can, but it can be also that I'm simply the combination. You see, I can have a very high rate, but the delta P can be low. So I can be outside the map for many different reasons. And I'm only allowed to use a combination of delta P and rates that are in this region. So our approach will be to we are not going to include the model of the ESP in our calculations. We are going to calculate the pressure just at the suction of the pump, the available pressure at the suction of the pump. We're going to calculate the required pressure at the discharge of the pump, calculated from the wellhead. And then we're going to calculate the delta H of the pump, and we're going to plot it, and we're going to see if it falls in the curve. So essentially, we simply are going to do exactly like what this plot indicated. We're going to calculate pressure available, pressure required. We're going to calculate the delta head of the pump with the rate, and then we're going to plot that into the performance plot. So let's start doing that. We have the rate is given. So the density will be simply the density of oil. Initially, there is no water breakthrough. We are producing only oil. I forgot to freeze it. The viscosity will be simply the viscosity of oil. Then with the rate that I force, I do the first step, which is to move from reservoir to bottom hole. For that, I'm going to use the IPR, a linear IPR, and what I want from the IPR is IPR PWF. I want to provide the pressure with the rate, with the productivity index, I freeze it, and reservoir pressure. And you see it's going down, but so far the bubble point pressure of the fluid is 30, so I have a value which is higher, it means that I don't have any gas, liberated gas. Q oil will be simply the total, and I don't have any water. Q total minus Q oil. P at the suction, remember we have flow in casing from the place where, from the perforation, from the place where the fluid goes into the wellbore, all the way to the suction of the pump. So to calculate that, we simply want to use, we are going to assume incompressible fluid, liquid, and we're going to use the Bernoulli equation. If we look at our BBA functions, single phase hydraulic, and you have here all the equations, but you have the ones that we are going to use are this P in or P out. P in is if you provide the pressure at the discharge of the pipe and you provide the rate, it calculates the pressure required at the inlet of the pipe. Pressure out tells you the pressure, calculates the pressure at the discharge of the pipe if you specify the rate and the pressure at the inlet of the pipe. So that's the one we want to use. We are moving now from the bottom hole all the way to the pump suction. So we want the pressure at that pump suction. If we look at the pipe, it's the casing, fluid entering into the bottom of into the perforation and then coming out in the reaching the pump. And you see essentially it's changing units for the rate, because the rate we have it in days, we need it in cubic meter per second. And then simply using this liquid pressure drop equation from Bernoulli equation. The friction factor is read here if it's laminar, and we have to be careful sometimes with oil, very viscous fluid, we might be actually in the laminar region. So that's the equation we are going to use. And remember, we are going to assume that local rate equal to standard condition rate. No, which is not true. We should have the volume factor. So we say P out, P at the suction of the pump. Let's see, what do we need? We need the rate. The inner diameter of the pipe will be D1. The density of the fluid, it might change, so I'm going to put it here. Viscosity, the length of that section, that's H1. The angle, here I have to remember what in what units. I think this was in, let's see, in degrees. So it's the inclination angle with respect to horizontal. So this should be 90. And here you have the conversion. The sine of, so let's try once more, P out, total rate, ID, freeze it, density, viscosity, the length. That will be, I don't have, it's, we're going to assume horizontal, even though it's not, we know it's not horizontal, we're going to assume horizontal. P in, it's the bottom hole pressure, and the roughness. Remember now, I like on the contrary to the gas case, now the roughness I can be in the regime where the roughness it's the uh, I'm not in the fully turbulent regime. I could be before. So roughness. Okay, I freeze it. P in angle, length, diameter. See, I froze. You see that pressure becomes smaller and smaller because it makes sense. The pressure, reservoir pressure, is also going down. But you see this pressure in this case, it's greater than 30. So at least in this case, I'm fulfilling this condition that it should be greater than 30 bar. The P at the discharge, so now I stop the suction, then I calculate the pressure required at the discharge. I move from separator. Remember, these are platform wells in Pellegrino. Okay, we have all the wells reach the platform and then they go very quickly to a manifold and to the separator, so you can assume that wellhead pressure is relatively constant. Chokes are either non-existing or fully open. And then you move from wellhead pressure to P discharge. Then for that we're going to use a P in function. The rate is the same rate. ID will be 0.14. Density, viscosity, length is now this guy. 90 degrees. P out, that P out is 7. And the roughness is here. It means that I have 76, but I need to go overcome all the losses from the discharge of the pump to the separator of 184. So that means I have a deficit of energy. Now let's see for all the rest. It remains more or less constant. Okay, here it was a mistake. Here we need to freeze this guy. So we have pressure at the discharge, pressure at the suction. So now we can calculate the delta P required by the pump, which will be the discharge. Let's make it positive, 107. Then we can calculate the head of the pump, which the head of the pump is delta P divided by the density of the fluid times the gravitational acceleration. Okay, but of course I need to change from bar, I need to change to pascals. So dividing the delta P of the pump across the pump by the density times the gravitational acceleration. After I have these points, I go and I plot them, the delta H and the Q, in the operational map of the pump. And I have to be sure that that these conditions, this is the actual viscosity of the fluid that the pump is handling. Can you see, initially I go 1700, but the delta P is increasing, or the delta H is increasing, 1200, 1400, 1500, 1700. And at that time, at that place, then I start to move to the left, which is still fine. I'm still within the area of operation, but then at some point it go below the minimum rate. But we see that almost all of our points are feasible. The only one is this, the last one. Okay, so let's keep that for now there. But um, then let's see, uh, let's calculate the power. So for the power, I mentioned also during our last lecture that the power has that equation. A hydraulic power is the delta P times the Q in units. It is in Pascal and this is cubic meter per second divided by the hydraulic efficiency. So we need our hydraulic efficiency. And if we want the motor power, we also need to include the mechanical efficiency because the motor has some losses due to also to friction in all the rotating components. So there we need to put a mechanical efficiency, and that's what we have given here. Mechanical efficiency is actually quite high compared to the hydraulic of 0.95. And then the pump the pump power usually is given in horsepower, so we need to have a conversion factor between watts because that equation in pure SI units gives me in watts, and then I have to change it to horsepower. So that equation is programmed um, for you here. Esp Power is that equation. Here I'm changing from Q from cubic meter per day to cubic meter per second, the efficiencies, and then that's the conversion factor from watt to horsepower. So let's see, the main thing is the hydraulic efficiency, and here I'm going to, so the hydraulic efficiency, I have to correct it to due to viscosity. We know that is here. Hydraulic efficiency looks like that, the curve, but then I have to correct it for viscosity. We're not going to go too much in detail how that's done. That's specified in these Hydraulic Institute guidelines, but we say viscosity, pump efficiency for viscous flow, and that's asking the Q, the rate that I have, the frequency. Okay, and the frequency, we haven't read the frequency yet. Let's see what are the approximate frequencies at which the pump will operate. So here it's, this is 60, this is 45, so it's maybe in between. That will be how much? Let's say 52.2, 52.5, sorry. Right? Because we are saying that that point will be in between these two lines. This is 45, this is 60, and then we say, well, it's more or less in this. Maybe we can put 52 or 51. Because half is 7.5 on each side, so here I might have like a bit less. So let's put 51. Then we move into that point. That point is actually closer to this one, so it might be is a bit higher than 52. Let's try maybe 50, 52.5, so it might be 50. Let's try with 54. The next point, this point is actually in between these two. I also like this point is to have the same frequency, so approximately. So I can say that's 52 plus 3.5. No, actually 52.5 plus 3.5, so that gives me 56. The same here. And then this one is maybe the same efficiency, the same frequency as this one, so it's 54. And the last one that we know is not going to work because it's outside the operational map. But let's put 52.5 and then we see if there is any way to fix it after we calculate the power. So now we have our estimated frequencies. These are read from the chart, which is not perfect, might have a lot of error. But if we're making this procedure as a visual inspection, that's really the only way to do it. If we program our pump equation and then we can estimate exactly how much will be the frequency. So efficiency, pump efficiency, viscous. Then I need the Q that is going through the pump, the frequency. Then the reference frequency, I have that in Esp performance. Then I block it. N is number of stages that the pump has. Density of the fluids that I have. Viscosity. Then comes the best efficiency point at the reference frequency. And that is at the reference frequency, the best efficiency point, the rate is here. Then comes all the coefficients for the head. They should be, I hope I'm blocking them. And then comes all the coefficients for the efficiency. C, D, E, F. Let's see, Q, F, 60, 78, 80.1, B, C, D, E, F, B, C, D, E, F. There is a mistake. No mistake. The only thing is that these efficiencies, they are in percentage. So we have to divide by 100 to get them in. So you have 40%, the maximum on that curve was 75%, but now we get much less because the fluid is viscous. It affects dramatically the performance of the pump. Then we go finally calculate the Esp power, and here we have the delta P of the pump. We provide the Q, we provide the mechanical efficiency, here is I want to have to freeze, and then the hydraulic efficiency. So let's summarize. We have taken a few years, 1, 2, 3, 4, 5, 6 years. We know that we are producing only oil, so we are lucky. We don't have to make any estimation of the mixture, of the emulsion, viscosity. We simply came and calculated the pressure available at the suction of the pump versus the pressure required for each year. And then we calculate the delta P required by the pump. Then we calculate the delta, the head of the pump required by the pump. We plotted those points. And then we saw that most of them, it's nice. Most of them fall inside the map, which remember the map is this guy here. Don't confuse with the full points. These are for water. But we have one point which falls outside, and then let's see if what can we do with that later. Then the next constraint was that the suction pressure had to be above of the pump, above 30, because we don't want any gas coming out of solution. So we said all of these are okay, but there are 3 years which are a bit critical. Then we read the frequencies because we need the frequencies for the efficiency. And then we did that as a visual approximation. We said, well, this is like half, a bit more than half. This is a quarter of this distance, and so forth. And after we have that, we calculate the efficiency. And I'm not going to go in details how this was done, but simply we use the procedure from the Hydraulic Institute. We have the efficiency curve at with water, 1 centipoise, and for a given reference frequency. So I have to make adjustments both for the frequency and both for the viscosity. And that gave me values around 50%. The pump power is these are these numbers, and if you compare them with 760, which is the maximum power that I can fit, or the maximum power that goes with that pump, 760, you see there are essentially 2 years in which that goes above the requirement. So how can I change that? Change reduce that power requirement. As I told you before, I can either try to put a bigger motor. In this case, it's not that big, it's 20 horsepower, so it might be possible to find a bigger motor for that application. This is a bit bigger, 40 horsepower, or if you don't have any other choice, you can try to reduce the rate for that year. So let's see if we reduce it slightly to 1600, for example. Okay, that was too much, 1750, sorry, 1650, 1670. In this case, I'm within the power constraint and I'm still able to produce quite close to the original rate. Then goes the next year, and that's essentially what I'm doing. It's on the two curves, I'm simply saying, well, I cannot deliver this rate. I'm going to go a bit to the left, then such that the delta P is less. And the power required is also less. And then let's go to the next year, let's say 1500. Okay, with 1500, 1490, probably I'm already within. But remember now I have to go on this chart and then change accordingly the frequency. The frequency will be slightly different. In this case, we have put 56, but maybe it could be 55, and this one might also be 55, which is still within the power required. Now let's go to the last try. So this point fell outside of the map. And how can we fix it? Well, if I increase the rate, right, I will bring it back to the map. That's essentially the only way that I can bring that point in, if I increase the rate. However, if I increase the rate, remember, if I go back to this diagram, I'm also going to increase the required pressure across the pump. Therefore, this point will go up like that. So I might be able, unlucky, to knock on the upper part of this curve, and the point won't be feasible anyhow. Depends on how it moves. So we can try to say, for example, 900. It's moving up. Let's try. Okay, and you see, it might be that that point we managed to bring it in if we change, for example, a bit more. And now it means it could be on the border, but is closer. The main problem that we see here is that we have another constraint, which is the suction pressure we should have at the inlet of the pump, mainly liquid, mainly oil. So you see that the pressure reduced at the suction dramatically to 2 bar, almost vacuum. So that means that I will have significant amount of gas liberating from the oil, and then that will cause a problem in the performance of the pump. So if I could calculate my GBF at those conditions and see how much gas I have liberated, and if it's above what is admissible, what is allowed, then I won't be able to flow that point. I could use a mixed impeller pump, which I have is more tolerant to gas, for example, but I won't be able probably to flow that point. Let's bring it back to what it had, something around 800. So the best solution here could be to to change the pump. At that particular point in time, at that particular year, you have to change the pump and use another model, which it doesn't give you such a high delta P, but it goes to lower rates. Essentially a smaller pump. Also, another solution could be, if possible, could be to lower. If I reduce this distance, the D1, because essentially the H1, 380 meters, if I lower the pump, it will be closer to the formation, and then that pressure will be higher, and then I might be able to produce that rate. But if not, there is no other choice. I have to go and make intervention and change the pump and put a smaller pump. That's the whole exercise. Thank you for watching.